A faint, invisible light fills every corner of the cosmos. This is the cosmic X-ray background, a ghostly glow of high-energy radiation discovered by accident in the 1960s. It is not the light of stars, but a pervasive whisper from the most violent events in the universe. To understand this signal is to read a secret history written in X-rays, a history of ravenous black holes, colliding galaxies, and perhaps even unseen particles. By the end of this exploration, you will know the 25 greatest mysteries this background light presents, puzzles that redefine our place in the cosmos. What creates this universal haze, and what forgotten chapters of cosmic violence does it conceal? The answers challenge everything we think we know about the fabric of space itself. What does it mean that our universe is forever glowing with a light we cannot see? This universal whisper was first heard by instruments never meant to listen. The story of the cosmic X-ray background begins not with a grand telescope, but with a simple, pointed question. Scientists in the 1960s wanted to study X-rays from the moon, a logical target. They launched small-sounding rockets, brief flights that carried detectors above Earth's atmosphere, which blocks these high-energy photons. What they found was not a lunar signal, but something far more profound. No matter where they pointed their instruments, the detectors registered a faint, steady hiss of X-ray light. It came from every direction, a uniform bath of energy painting the entire sky. This was the first detection of the diffuse glow, and it posed an immediate and monumental mystery. Where was this light coming from? The central question became one of scale and source. Was this glow the combined light of countless individual, incredibly distant cosmic objects, like a distant city whose countless streetlights blur into a single haze from far away? Or was it something else entirely, a truly diffuse phenomenon woven into the fabric of space itself, a fundamental property of the universe? The prime suspects were the most powerful engines known, active galactic nuclei. These are supermassive black holes at the hearts of galaxies, consuming matter with such ferocity that they blast out X-rays across cosmic distances. If there were enough of them spread across the entire observable universe, their combined light could perhaps create this background haze, but for decades, technology could not provide an answer. This was the great resolution problem. The glow was so faint and uniform that telescopes of the time could not pick out the individual points of light within it. It was like trying to distinguish individual raindrops in a downpour from a mile away. The mystery hung in the air, unresolved for a generation. Was the cosmos filled with uncountable hidden monsters, or were we seeing the echo of a single, vast and unknown event? The answer would finally come from the eyes of a new generation. For decades, the cosmic X-ray background was just that, a background, an impenetrable fog. Then, in the late 1990s and early 2000s, two powerful observatories, Chandra and XMM Newton, were launched. Their mission was clear: to stare deeply into that fog with unprecedented sharpness and sensitivity. What they saw changed everything. The uniform glow began to fracture. It resolved into millions upon millions of individual, brilliant pinpricks of light. Each one was an active supermassive black hole, a cosmic engine screaming its existence across billions of light years. The analogy of the distant city was proven correct. The background was not a fundamental property of space, but the accumulated light of countless distant monsters. This was a monumental discovery, solving one great mystery by confirming the primary source population. But in doing so, it unveiled a deeper, more subtle puzzle. Even with their incredible vision, Chandra and XMM Newton could not account for all the light. A stubborn fraction of the background, perhaps 20 to 30%, refused to be resolved into individual points. It lingered as a true, diffuse haze. So what is creating this leftover glow? the leading theory points to populations of sources so incredibly faint or so deeply shrouded in dust that even our best telescopes cannot pick them out individually. We are talking about the earliest, most distant black holes in the universe, ones that are growing slowly or are obscured by thick cocoons of gas. Their light is so stretched and dimmed by the expansion of the universe that it blends into the background noise. But there is another, more exotic possibility. Could some of this unresolved signal come from something entirely different, like the decay of hypothetical dark matter particles? The fact that we cannot pinpoint the source of every last photon means our census of the cosmos is still incomplete. A shadow population of cosmic objects, or perhaps something stranger, is still out there, its signature woven into that faint, universal whisper. This unresolved whisper may hold the key to finding something the universe has lost. We are not talking about dark matter or dark energy, but something far more familiar, the ordinary atoms that make up stars, planets, and us. Cosmologists have a precise inventory of all the normal matter, called baryons, that should have been created in the Big Bang. Yet when they count all the visible stars, galaxies, and cold gas clouds, more than half of that expected matter is simply missing. This is the great missing baryon problem. Where did half the atoms in the universe go? The leading theory is that they are not in bright, compact objects, but spread out in an immense, delicate web. This is the cosmic web, a vast network of hot, thin gas filaments stretching between galaxies and clusters. This gas is so incredibly diffuse and scorchingly hot, heated to millions of degrees by the gravitational pull of the web itself, that it does not glow in visible light. But at those temperatures, it should emit a faint shimmer of X-rays. This is where the cosmic X-ray background offers a possible solution. That stubborn, unresolved portion of the glow we cannot attribute to black holes could be, in part, the collective murmur of this missing matter. It would be the accumulated X-ray whisper from every filament in the cosmic web, a faint signal from the universe's hidden skeleton. Proving this is immensely difficult, as distinguishing this specific signal from other sources is like trying to hear a single instrument in a symphony played from another city. But if we can learn to read that specific signature within the background's haze, we will have finally found the universe's lost atoms, tracing the architecture of all creation through a ghostly X-ray glow. But to truly hide a cosmic monster, you need more than just distance. You need a cloak. This brings us to a deeply hidden population that could solve the mystery of the unresolved background, the heavily obscured active galactic nuclei. Imagine the most powerful engine in the universe, a supermassive black hole feasting on matter. Now picture it not as a brilliant beacon, but buried at the heart of a thick, swirling donut of dust and gas. This is an obscured active galactic nucleus. The physics here is crucial. As matter spirals toward the black hole, it releases torrents of high-energy X-rays. But if the black hole is shrouded in that thick cocoon, those X-rays do not escape directly. Instead, they slam into the surrounding dust and gas, which absorbs the energy. That energy does not just vanish, it is re-emitted, but at much lower, less penetrating energies like infrared light. From our perspective, the brilliant X-ray scream of the black hole is muffled into a faint, warm whisper. This makes these objects incredibly difficult to find with standard X-ray telescopes. They are the cosmic equivalents of a lighthouse shrouded in dense fog, its powerful beam reduced to a dim, diffuse glow. These hidden monsters could be everywhere, a vast population we have barely begun to census. If they are numerous enough, their combined, muffled X-ray output could account for a significant portion of that stubborn, unresolved haze in the cosmic X-ray background. We need a telescope that can see through the fog. That is the mission of new STR, the Nuclear Spectroscopic Telescope Array. Unlike observatories that see lower-energy soft X-rays, new STR is designed to detect the highest-energy hard X-rays. Think of it this way: soft X-rays are like light rain, easily blocked by an umbrella of dust. Hard X-rays are like heavy bullets. They can punch through that obscuring material. By peering into this hard X-ray regime, new STR acts as a cosmic piercer of veils. It is finding these shrouded black holes in surprising numbers, revealing that the universe may be teeming with hidden giants we never knew were there. Each discovery helps chip away at the unresolved background, turning a uniform mystery into a catalogue of hidden lives. But the universe's X-ray symphony has more than one section of the orchestra. While supermassive black holes dominate the distant chorus, there is a different, more local rhythm at play. We must consider the stellar mass black holes and neutron stars, the collapsed remnants of massive stars that died in supernova explosions. These are not the billion solar mass giants at galactic centers, but objects typically weighing between 5 and 20 times the mass of our Sun. On their own, they are far less luminous than an active galactic nucleus. But they rarely perform solo. Often they exist in binary systems, locked in a gravitational dance with a normal star. And here the drama unfolds. The intense gravity of the black hole or neutron star can strip material away from its companion star. This stolen gas does not fall quietly. As it spirals inward at tremendous speed, it forms a searingly hot disk of plasma, a cosmic whirlpool that glows fiercely in X-rays before vanishing past the event horizon. These systems are called X-ray binaries, and they are scattered throughout galaxies, including our own Milky Way. They are the brilliant, flashing beacons of stellar graveyards. So, do these countless local flashes add up to a significant part of the cosmic X-ray background? The answer is a fascinating puzzle of perspective. Because X-ray binaries are found inside galaxies, their light is not spread evenly across the cosmos. From our vantage point within the Milky Way, we see nearby binaries as bright, individual points. But when we look out into the deep universe towards other galaxies, the combined light of all the binaries within those distant islands blends together. It becomes a faint, diffuse glow emanating from the galactic disks themselves. This presents a critical question for cosmologists. Is the background we measure truly isotropic, meaning perfectly uniform in all directions? Or does it contain subtle variations that trace the large-scale structure of galaxies? If stellar binaries contribute significantly, we might expect the background to be slightly brighter when we look in directions where more galaxies are clustered together, and slightly dimmer in the voids between them. Distinguishing this signal is like trying to hear if the hum of a distant city changes when you face different neighborhoods. Current research suggests that while these stellar remnants are important local X-ray sources, their collective contribution to the truly uniform, all-sky background is minor compared to the accumulated might of billions of supermassive black holes across cosmic time. They are the percussion section in our own galactic neighborhood, vital and energetic, but not the source of the deep, universal hum that fills the void. Yet another diffuse glow arises from the largest structures gravity can build. Between the brilliant points of active black holes and the faint hum of the cosmic web lies a third major contributor to the universal X-ray haze, the galaxy clusters themselves. These are not mere collections of stars, but the metropolises of the cosmos, vast gravitational domains containing hundreds or even thousands of galaxies. What truly defines them, however, is not the galaxies, but what lies in the immense spaces between them. The clusters are filled with an ocean of superheated gas, a plasma so thin it is a better vacuum than any we can create on Earth, yet so incredibly hot it glows at temperatures of tens of millions of degrees. This heat comes from a simple, violent source. As the cluster formed over billions of years, ordinary gas fell into the immense gravitational well created by the cluster's immense dark matter halo. That gas did not fall gently. It plunged inward at nearly the speed of light, colliding and compressing, its gravitational energy converted directly into blistering heat. This trapped, seething ocean is known as the intracluster medium, and it is the hottest, most massive thing in the universe that we can directly observe. And at those phenomenal temperatures, it shines brightly in X-rays, creating a vast, diffuse halo that can be larger than the galaxies it surrounds. So, what is its role in the cosmic X-ray background? When we look at a single, nearby cluster like Virgo or Coma, its X-ray halo is a distinct, brilliant object. But when we look across the entire universe, the combined light from every cluster's hot gas blends together. It adds another layer to the all-sky hum. Calculating this contribution is a complex task of cosmic accounting. Astronomers must estimate the total number of clusters across cosmic history, measure the typical brightness and size of their hot gas halos, and sum it all up. Current estimates suggest that while significant, this hot intracluster gas is not the dominant player. It might contribute roughly 10 to 20% of the total background's intensity. Its story, however, is not static. It evolves dramatically over cosmic time. In the early universe, clusters were still assembling. Their gravitational wells were shallower, so the gas within them was cooler and less concentrated, meaning it emitted fewer X-rays. As the universe aged and clusters grew through mergers and accretion, their gravitational grips tightened. The intracluster gas was compressed and heated to even more extreme temperatures, causing its X-ray output to increase. So the contribution of clusters to the background is not a constant number, it is a curve that rises with time. This creates a fascinating fingerprint within the background's light. The specific X-ray energy or color of the light from this hot gas carries the signature of its temperature. By carefully dissecting the background spectrum, scientists can, in principle, search for the integrated glow of all the cluster gas that has ever existed. It is like listening to a recording of a forest and trying to pick out the specific rustle of leaves from every oak tree that has ever grown. A monumental task that requires separating one universal whisper from another. This search tells us not just about the gas itself, but about the entire growth history of the cosmic web's densest knots, written in a light we cannot see. The deepest mysteries are often written in the language of extremes. As we dissect the cosmic X-ray background, we find its most puzzling component is not the bulk of its light, but its faint, high-energy tail. This is the realm of the hardest X-rays, photons carrying so much punch they border on gamma rays. They represent the most violent processes in the universe, a whisper of pure cosmic fury. Their existence forces us to ask, what natural engine can possibly accelerate particles to such unimaginable speeds? The leading candidates are cosmic shockwaves of almost incomprehensible scale. Picture the aftermath of a galaxy cluster collision, the largest explosion since the Big Bang itself. When two of these titanic structures merge, they do not simply pass through each other. Their immense clouds of hot gas slam together, creating shock fronts that race through space at millions of miles per hour. These are particle accelerators on a cosmic scale, far more powerful than anything on Earth. Charged particles like electrons and protons get caught in these turbulent magnetic fields and are whipped back and forth, gaining tremendous energy with each pass. When these ultra-relativistic particles finally collide with photons or magnetic fields, they can spit out the very high-energy X-rays we detect in the background's tail. Similarly, the expanding blast waves from supernova remnants within our own galaxy and others serve as smaller, but incredibly efficient particle accelerators. But there is a profound problem. When scientists add up the expected contribution from all the known shockwaves in clusters and supernova, the numbers often fall short. The observed high-energy tail seems just a bit too bright. This discrepancy opens the door to far more speculative and thrilling possibilities. Could some of these ultra-hard photons be the signature of dark matter itself? Certain theoretical models suggest that if dark matter is made of weakly interacting massive particles, these particles could occasionally annihilate with one another or decay. Such an event would be a burst of pure energy, potentially releasing high-energy gamma rays and X-rays. If this is happening throughout the universe, in every galaxy and halo, it would contribute a faint, nearly uniform glow to this hardest part of the spectrum. Detecting such a signal is the ultimate challenge, like trying to hear a specific note played on a single violin within the roar of a hurricane. It requires meticulously subtracting every other known source of emission, from distant black holes to hot cluster gas, to see if an unexplained residue remains. The hunt is on because within that faint, energetic tail of the background could lie the first indirect evidence of the universe's dominant, yet invisible component. It is a ghost potentially leaving fingerprints in the most energetic light we can see. To understand the present, we must listen to two different echoes of the past. The universe speaks to us in two fundamental whispers, each telling a separate chapter of its epic story. The first is the cosmic microwave background, the oldest light we can see. It is a snapshot of the infant universe, a mere 380,000 years after the Big Bang, when everything was a hot, dense, nearly uniform soup of particles and energy. As the universe expanded and cooled, that light stretched into the microwave part of the spectrum, becoming a faint, cold glow that bathes the entire cosmos. It is a fossil, a pristine record of the universe's smooth, featureless beginnings. The cosmic X-ray background is its polar opposite. It is not a single snapshot, but a layered, cumulative exposure. It is not the light of a smooth beginning, but the light of a violent, structured maturity, where the microwave background shows us a universe before stars or galaxies. The X-ray background is the direct result of everything that came after. It is the combined afterglow of every supermassive black hole that ever feasted, every galaxy cluster that ever collided, every shockwave that ever raced through space. Think of it this way: the cosmic microwave background is a baby picture of the cosmos, showing its original, unblemished state. The cosmic X-ray background is a time-lapse film of its entire life, capturing every growth spurt, every collision, every energetic outburst across billions of years. One shows us the blank canvas, the other shows us the finished, chaotic, and magnificent painting. This comparison reveals the true nature of the X-ray glow. It is not a background in the same primordial sense. It is a living history book, a dynamic archive of structure formation. Every photon in that haze has been emitted by something hot, something violent, something that gravity has sculpted from the smooth conditions of the early universe. By studying its intensity and its spectrum, we are not looking at a single moment, but reading a biography. We can trace how the first supermassive black holes ignited and grew, how galaxies gathered into clusters, how the cosmic web heated up. The microwave background tells us how the story started. The X-ray background tells us everything that happened next, yet that universal hum is not perfectly uniform. If you could listen with impossibly sensitive ears, you would hear subtle ripples and variations in the X-ray whisper. These tiny fluctuations are called anisotropies, and they are not flaws in the signal, they are its most valuable feature. They are the cosmic X-ray background's way of casting a shadow play of the universe's largest structures. Think of it like this: you are standing in a dense fog that glows with a faint, even light. If that fog were truly uniform, you would see nothing but a blank, luminous gray in every direction. But if there are slight differences in the fog's thickness, if it is a bit denser in some areas and thinner in others, those areas will appear slightly brighter or dimmer. Your eyes would begin to trace out shapes in the mist, revealing the hidden landscape around you. The anisotropies in the X-ray background work the same way. The glow is not a perfectly smooth paint job across the sky. There are minute variations in its brightness, tiny dips and rises that are incredibly difficult to measure. What causes these variations? They trace the underlying cosmic web, the vast architecture of the universe. Where galaxies and massive clusters are densely packed together, there is more hot gas in the intracluster medium and more supermassive black holes in active galactic nuclei. These crowded regions, these knots and filaments in the cosmic web, contribute more X-rays to the overall haze, so when we look in their direction, the background is ever so slightly brighter. Conversely, when we look into the immense voids, the empty deserts of space where matter is scarce, there are far fewer X-ray sources. The background in that direction is fainter. By meticulously mapping these incredibly subtle brightness variations across the entire sky, astronomers are effectively creating an X-ray map of the large-scale structure of the universe. This is a completely different perspective than we get from optical telescopes. Optical surveys see the starlight from galaxies, tracing where the stars are. An X-ray anisotropy map sees the hot gas and the violent black holes, tracing where the most energetic processes are happening. It is the difference between mapping a city at night by seeing its streetlights and mapping it by sensing the heat radiating from its power plants and engines. Both are valid maps of the same city, but they reveal different aspects of its function and structure. This hot gas perspective is crucial for cosmology. It helps us test our models of how the cosmic web formed and evolved under the influence of gravity and dark energy. It provides an independent check on measurements from the cosmic microwave background and optical galaxy surveys. By comparing these different maps of the same cosmic landscape, we can uncover inconsistencies or confirm our theories, building a more complete and reliable picture of the universe's skeleton. Each faint ripple in the X-ray glow is a clue, a single brushstroke in a pointillist painting that reveals the hidden architecture of all existence. That faint X-ray hum is a historical document, its pages written in light across billions of years. The cosmic X-ray background does not show us a single moment, but a layered chronicle of violence and growth. To read it, we must understand how its primary authors, the active galactic nuclei, have changed over cosmic time. Their story is not one of constant activity. Instead, it follows a dramatic arc, a rise and fall that has left a permanent imprint on the universal glow we measure today. The plot reaches its climax during a period astronomers call cosmic noon. This was not a brief event, but an epoch spanning from roughly 10 to 3 billion years after the Big Bang, when the universe was in its vibrant, tumultuous adolescence. During cosmic noon, conditions were perfect for supermassive black hole feasting. Galaxies were gas-rich, collisions and mergers were frequent, and vast reservoirs of fuel were funneled into galactic centers. This triggered an explosive era of growth, turning black holes into brilliant quasars and active galactic nuclei that shone with ferocious intensity. The universe was lit up with X-ray beacons. This peak of activity is directly encoded in the background we observe. Because light takes time to travel, when we look out into deep space, we are also looking back in time. The X-ray photons from the most distant active galactic nuclei, those shining at cosmic noon, are only just reaching us now. Their light has been stretched and diluted by the expanding universe, but their immense numbers from that frenzied epoch contribute a massive portion of the total background's intensity. Think of it as listening to a recording of a great concert. The loudest applause, captured from the peak of the performance, still dominates the recording even after the hall has emptied. The background is that recording, and the roar from cosmic noon is the applause we still hear. But the story has a later, quieter chapter. After cosmic noon, the universe began to settle. Major mergers became less common, and the readily available gas in galaxy cores was either consumed or blown away by the intense radiation from the black holes themselves. The great feasts ended. Active galactic nuclei became rarer and generally less luminous. Their contribution to the ongoing X-ray output of the universe declined. This evolution from a roaring peak to a present-day murmur creates a specific signature in the background's light. It means the glow we see is not equally contributed by every era of cosmic history. It is heavily weighted toward that ancient, violent noon. By carefully analyzing the spectrum of the background, scientists can perform a kind of cosmic archaeology. They can attempt to disentangle the relative contributions from active galactic nuclei at different distances and therefore different ages. This allows them to reconstruct the history of black hole growth and activity, not by finding individual objects but by reading the summed light of all of them. It confirms that the supermassive black holes we see quietly lurking in nearby galaxies today are the dormant descendants of brilliant monsters that once ruled a younger, wilder cosmos. Their faded glory still whispers to us a permanent echo in the X-ray haze. Buried within that universal hum are spectral fingerprints that simply do not belong. As scientists dissect the precise energy signature of the cosmic X-ray background, they find more than just a smooth continuum of light. They detect faint, sharp spikes at specific wavelengths called emission lines. These are the telltale signatures of specific atomic elements like cosmic barcodes. Hot iron gas, for instance, emits a very distinct line that we see in many astrophysical sources. The problem is that some of the lines seen in the background spectrum do not match any known element on the periodic table. They are unidentified, ghostly signals with no obvious parent. This is not a case of blurred or noisy data. These are precise energies with no known atomic transition to explain them. Their very existence points to something emitting X-rays in a way we do not yet understand. One of the most tantalizing candidates is a particle that has never been directly detected, the sterile neutrino. This is a hypothetical cousin to the ordinary neutrinos that flood the universe. Unlike its relatives, a sterile neutrino would not interact through the weak nuclear force at all, making it incredibly difficult to find. However, according to some theories, it could be slightly unstable. If it exists, a sterile neutrino might occasionally decay into an ordinary neutrino and a photon, an X-ray photon at a very specific, predictable energy. If sterile neutrinos are abundant throughout the cosmos as a form of warm dark matter, their collective decays could produce a faint emission line that would appear uniformly across the sky, woven directly into the fabric of the X-ray background. Finding such a line would be a monumental dual discovery, revealing both the nature of dark matter and a fundamental new particle. Other possibilities are less exotic but equally mysterious. The lines could come from previously unknown states of matter in the seething plasmas of galaxy clusters or around black holes, perhaps under conditions of extreme density and magnetic field. Atoms behave in ways our laboratory physics has not yet charted, emitting light at energies we cannot predict. Or they could be the signature of an entirely new type of astronomical object we have not yet classified. Each unidentified line is a direct challenge, a piece of evidence that our catalogue of cosmic ingredients is incomplete. They are not just mysteries, they are signposts. They point unequivocally to gaps in our understanding of particle physics or astrophysics, gaps that the serene, all-sky glow of the X-ray background has the unique power to illuminate. That ghostly X-ray line is just one color in a far broader spectrum of universal light. To truly appreciate the scale of the cosmic X-ray background, we must step back and see it in its proper context as part of the universe's total energy budget. This is the extragalactic background light, a concept as grand as it sounds. It is the sum total of all the photons, from the longest radio waves to the most energetic gamma rays, that have ever been emitted by every star, galaxy, and cosmic engine since the dawn of time, now freely traveling through intergalactic space. Picture every light source that has ever shone, its radiation stretched and diluted by the expanding cosmos, blending into a faint, multi-wavelength glow that fills the void. The cosmic X-ray background is one crucial chapter in that immense electromagnetic encyclopedia. Think of the universe's total radiative output like the energy consumption of a vast, ancient city. The starlight from all the galaxies, the optical and infrared glow, is like the power used for lighting homes and streets. It represents the steady, ongoing fusion processes in countless suns. It is the dominant form of energy, the baseline hum of normal stellar life. The cosmic microwave background is the foundational energy left over from the city's explosive founding, a relic heat that still permeates everything. And then there is the X-ray background. This is not the power for streetlights. This is the energy consumed by the city's heavy industry, its power plants, and its most violent demolition sites. It represents the high-energy, transformative processes, matter torn apart near black holes, gas heated to millions of degrees in cluster collisions, particles accelerated in colossal shock waves. It is a far smaller portion of the total energy budget than starlight, but it is arguably the most dynamic and informative. This comparison reveals a critical balance. The energy locked in the X-ray background must have come from somewhere. Ultimately, it is gravitational energy. When matter falls into a black hole or plunges into a galaxy cluster's gravitational well, its potential energy is converted into the intense radiation we detect as X-rays. This means the X-ray background is a direct ledger of the universe's gravitational history. It tells us how much mass has been processed through these extreme environments over cosmic time. By measuring its total intensity and comparing it to the energy in starlight and the microwave background, cosmologists can check the books of the cosmos. Do the numbers add up? Does the gravitational energy released in creating structures match what we see in this high-energy glow? So far, the accounting seems consistent, a reassuring sign that our broad understanding of cosmic evolution is on track. But the precise value of the X-ray background's contribution is a key number in that calculation, a number we are still refining. A slight discrepancy here could point to missing sources of energy or errors in our timeline of when structures formed. This integrated view across all wavelengths also solves practical mysteries. For astronomers studying distant, brilliant objects like gamma-ray bursts or blazars, the extragalactic background light is not just a curiosity, it is a fog. Those highest energy gamma rays traveling across billions of light-years can collide with lower energy photons from the background light, such as optical or infrared photons, and be absorbed. They never reach our telescopes. The X-ray background is part of this intervening fog. By understanding its precise density and distribution, we can better calibrate our observations of the most violent events in the distant universe, correcting for the light lost along the way. It is a reminder that the universe is not perfectly transparent. It is filled with the faint, accumulated echoes of its own history, and every photon we seek to study must travel through that haunted medium. The X-ray whisper is both a signal we study and a veil we must see through, a fundamental part of the cosmos's luminous tapestry. Among the brilliant points of light that make up the background, a special class screams with unmatched ferocity. These are blazars, a rare and extreme type of active galactic nucleus. Their power comes from a cosmic accident of alignment. At the heart of a blazar lies a supermassive black hole, but unlike other active galaxies, this monster is firing a pair of relativistic jets, beams of particles and radiation traveling at nearly the speed of light, and one of those jets is pointed almost directly at our line of sight. This changes everything. The physics of relativity tells us that when an object moves toward us at such a tremendous fraction of light speed, its radiation gets boosted, amplified, and squeezed into a much shorter wavelength. It is like the sonic boom of a jet plane, but for light. This effect, called relativistic beaming, takes the already intense emission from the jet and focuses it into a brilliant, tightly beamed searchlight. From our privileged and slightly dangerous vantage point staring right down the barrel, that searchlight appears extraordinarily bright across the entire electromagnetic spectrum, from radio waves to gamma rays. In X-rays, they are some of the most luminous and violently variable objects we know, flickering and flaring on timescales of days or even hours. So with all that power, could blazars be the hidden key to the unresolved cosmic X-ray background? The challenge is one of geometry and statistics. Because their incredible brightness depends on that precise alignment, blazars are incredibly rare. For every one we see blazing directly at us, there must be hundreds or thousands of similar active galactic nuclei with jets pointing in other directions, appearing much fainter to our telescopes. When scientists try to add up the total X-ray light from all the blazars across the universe, accounting for this beaming effect and their rarity, they find something fascinating. Blazars are so individually bright that they contribute a significant chunk, perhaps around 10 to 15% of the total X-ray background, but they cannot explain the lingering, truly diffuse, unresolved glow. Their light is still fundamentally point-like. Our best telescopes can, and do, resolve individual blazars as distinct dots in the X-ray sky. They are not the source of the uniform haze. Instead, they present a different kind of puzzle. Their extreme variability creates a flickering component to the background's light. If you could take an ultra-fast movie of the X-ray sky over years, you would see blazars flashing on and off like cosmic strobe lights against the more steady glow of other active galactic nuclei and hot gas. This flicker itself is a tool. By studying how the collective blazar light varies, astronomers can probe the demographics of these beamed monsters throughout cosmic history. It helps answer questions like, how common were these perfectly aligned jets in the early universe? Did the conditions for creating such precise, powerful beams change over time? So while blazars are not the secret source of the unresolved background, their amplified whisper forces us to consider the role of chance and perspective in the cosmos. We are witnessing a select few engines in their most extreme, head-on presentation, a reminder that the universe's violence is often directional, and we just happen to be in the line of fire for a lucky or unlucky few. But the spectrum of this cosmic whisper holds a curious imbalance. As scientists dissect the precise energy makeup of the cosmic X-ray background, they find a puzzling surplus at the lower end of the scale. This is the mystery of the soft X-ray excess. Soft X-rays are the lower energy cousins of the hard X-rays that punch through dust, less penetrating but far more abundant in this particular measurement. According to our best models of distant black holes and hot cluster gas, there should not be quite so many of these softer photons, yet the data shows a clear, persistent excess, a gentle hum within the louder roar. Where is this extra light coming from? The suspects are intriguingly close to home. The first is a vast local structure known as the local bubble. Our solar system is not floating in a uniform, cold void. We reside inside a cavern of hot, thin gas, a region roughly 1,000 light-years across, carved out by ancient supernova explosions that occurred millions of years ago. This gas, while incredibly diffuse, is hot enough to emit soft X-rays. It essentially creates a luminous fog bank that surrounds our entire solar neighborhood. When our telescopes look out, they see the distant cosmic background through this fog, and its glow is added to everything else, potentially accounting for a significant portion of the soft excess. The second suspect operates on an even smaller scale, right here in our own solar system. It involves a process called charge exchange. The sun constantly blows out a stream of charged particles, the solar wind. When these high-speed protons and ions encounter neutral gas, like the sparse atoms of hydrogen that float in from interstellar space, they can steal an electron. This theft is not gentle. The captured electron drops into a lower energy state around the new nucleus, and in doing so, it releases a photon, often a soft X-ray. This process creates a faint, all-sky glow that originates just beyond the planets, a shimmering X-ray aurora enveloping our entire solar system. Both the local bubble and solar system charge exchange are foreground effects, local fog that contaminates our view of the true cosmological signal. If they are the sole culprits, then the soft excess is not a deep mystery of the cosmos, but a reading error, a case of our own backyard interfering with the signal. But what if, after carefully subtracting these local contributions, a stubborn, soft excess remains? This is where the mystery turns profound. That leftover glow could be the first direct detection of the universe's missing matter in a specific state. It might be the signature of the warm-hot intergalactic medium, the WHIM. This is the theorized web of gas filaments, not in the ultra-hot cores of clusters, but in the moderately warm outskirts, heated to hundreds of thousands of degrees. At these temperatures, gas emits strongly in soft X-rays. Finding its signal would be the ultimate validation of the missing baryon theory, proving that half the atoms in the universe are indeed hiding in this vast, warm web. The great debate continues. Is the soft excess just local fog, or is it the faint, universal glow of the cosmic web itself? The answer requires painstaking work, mapping the exact pattern of the excess across the sky. If it is perfectly uniform, it points to a cosmological origin like the WHIM. If it shows patterns aligned with the structure of our local bubble or the movement of the solar wind, then it is a local phenomenon. Currently, the evidence points strongly to local sources dominating the signal, a reminder that to see the distant universe clearly, we must first understand the intricate glowing shell of our own celestial home. The universe is filled with sudden, brilliant screams. Among the most spectacular are tidal disruption events, cosmic cataclysms of singular violence. Picture a star similar to our own Sun on a routine orbit through its galaxy. Its path takes it too close to the supermassive black hole lurking at the galactic center. The difference in gravitational pull between the side of the star nearest the black hole and the side farthest away becomes overwhelming. This tidal force stretches the star, pulling it apart like taffy in a process called spaghettification. The star is shredded into a long, thin stream of gas. Much of this stellar debris then swirls into a searingly hot accretion disk around the black hole, where it is heated to millions of degrees before vanishing over the event horizon. This process unleashes a tremendous flash of radiation, a flare that can outshine its entire host galaxy for months, blazing brightly across the electromagnetic spectrum, including a powerful burst of X-rays. It is a black hole's single, glorious feast, a beacon announcing a star's destruction. These events, while incredibly dramatic, are also quite rare. In a typical galaxy, a tidal disruption event might happen only once every 10,000 to 100,000 years. So the question becomes, with such infrequency, could they possibly contribute to the steady, all-sky hum of the cosmic X-ray background? It seems counterintuitive. How could something so rare and brief add up to a permanent whisper? The answer lies in the vast scale of the observable universe. While one galaxy might witness a tidal disruption event only once in an epoch, the cosmos contains upwards of 200 billion galaxies. Across all of space and time, these stellar deaths are happening constantly. From our perspective, they are not synchronized. While one flare fades in a distant galaxy, another is just beginning in a galaxy on the opposite side of the sky. The integrated light from all these individual scattered cataclysms could, in theory, blend together into a faint, diffuse component of the background glow. Calculating this contribution is a delicate exercise in cosmic statistics. Astronomers must estimate the average rate of these events per galaxy, the typical brightness and duration of their X-ray flare, and then multiply that by the total number of galaxies across cosmic history. Current models suggest that while tidal disruption events are brilliant, their overall contribution to the X-ray background is likely small, perhaps less than 1%. They are the cosmic equivalent of camera flashes going off in a vast, dark stadium. Individually, each flash is blinding, but their combined sporadic light does little to illuminate the entire arena. However, their value is not in their summed power, but in their unique signature. These events offer a direct, clean probe of otherwise dormant supermassive black holes. In a quiet galaxy with no active nucleus, a tidal disruption event suddenly reveals the hidden monster at its heart, allowing us to study its mass and properties. Furthermore, the specific shape and evolution of the X-ray light from such a flare carries information about the type of star destroyed and the physics of the accretion process in real time. So while they may not solve the mystery of the unresolved background, tidal disruption events are crucial punctuation marks in the universe's narrative. They remind us that the cosmic hum we hear is not just the sound of steady engines, but also the accumulated echo of countless individual catastrophic moments, each a star's final, brilliant cry woven into the fabric of the silent dark. To see the true cosmic whisper, we must first see through our own galactic fog. This is the challenge of galactic absorption, a pervasive foreground effect that complicates every measurement of the faint X-ray background. Our Milky Way is not an empty window to the wider universe. It is filled with an interstellar medium, a sparse but vast mixture of gas and dust that drifts between the stars. While this material is transparent to our eyes and to high-energy X-rays, it acts like a subtle filter for the lower-energy, soft X-rays. The physics is straightforward. A soft X-ray photon traveling from a distant quasar or hot gas filament has a certain probability of interacting with a neutral atom, like hydrogen or helium, in our galaxy's interstellar medium. When it does, the photon can be absorbed, its energy taken up by the atom, or it can be scattered, deflected onto a different path. Either way, that particular photon from the distant cosmos never reaches our telescope. It is lost, dimming and reddening the light from beyond our galaxy, much like a thin haze dims the colors of a distant mountain range. This creates a fundamental problem for cosmologists. The signal they are trying to measure, the extragalactic cosmic X-ray background, is always viewed through this shimmering, absorbing veil of our own galaxy. To isolate the true cosmological signal, astronomers must build incredibly detailed models of this galactic fog. They must map the three-dimensional distribution of neutral gas throughout the Milky Way, estimate its temperature and density, and calculate precisely how much soft X-ray light it should be absorbing and scattering from every direction on the sky. This model is then subtracted from the total observed signal. What remains, in theory, is the pristine light from the distant universe, but this process is a major source of uncertainty, especially at the softest X-ray energies where absorption is strongest. The models depend on imperfect maps of galactic hydrogen, and they assume we understand the exact interaction between X-rays and interstellar atoms under a wide variety of conditions. If the model is even slightly wrong, if it underestimates the gas in a particular line of sight, then the subtracted signal will be incorrect. We might think we are seeing a faint patch in the extragalactic background, when in reality we are just looking through a slightly thicker patch of our own galactic fog. Conversely, over-subtracting the galactic contribution could create an artificial excess, making us believe we have detected a new cosmological signal when we have not. This uncertainty is why debates about the origin of the soft X-ray excess are so difficult to resolve. Is an observed surplus of soft photons a genuine feature of the warm-hot intergalactic medium? Or is it merely an artifact of imperfectly modeling the local bubble and the Milky Way's own interstellar haze? The answer requires painstaking multi-wavelength observations to cross-check the gas maps and a constant refinement of the subtraction algorithms. It is a reminder that the universe's deepest secrets are never handed to us directly. They are always encrypted, and the first layer of the code is written in the faint, absorbing mist of our own celestial home. This very challenge of galactic fog reveals a profound irony about the X-ray whisper. Astronomers struggle to see past our own galaxy to measure the cosmic X-ray background accurately, yet they must rely on its assumed properties to see anything at all. This is the circular puzzle of calibration. For an X-ray telescope floating in space, there is no simple light bulb to use as a reference, no cosmic candle with a known fixed brightness. Instead, scientists use the background itself as their standard lamp. They point their instrument at a seemingly blank patch of sky, far from any known bright source like a star or a galaxy cluster. The count of photons that arrive, that steady, faint hiss, is assumed to be the uniform glow of the distant background. This measured count rate becomes the baseline. It tells engineers whether the telescope's detectors are performing as expected, if their sensitivity has degraded over time, or if a software update has inadvertently changed how they count light. It is a masterstroke of practical astronomy, using the universe's own diffuse glow as a tool to sharpen our vision, but the circularity is immediate and profound. We are using the cosmic X-ray background to calibrate the very instruments we need to understand the cosmic X-ray background. We must assume it is smooth and predictable to measure it, but the goal of measuring it is to discover its irregularities and secrets. This creates a delicate, self-referential loop. If the background is not perfectly uniform in the patch of sky chosen for calibration, if there is an unseen cluster of faint galaxies or a wisp of the warm, hot intergalactic medium, then the calibration is slightly off. That tiny error then propagates into every other measurement the telescope makes. It could make a distant quasar appear a fraction brighter or dimmer than it truly is, skewing our models of how black holes evolve. It could mask a genuine anisotropy or create a false one. To break this circle, astronomers employ a clever strategy of cross-calibration. They will point multiple different X-ray observatories like Chandra, XMM Newton, and Swift at the same empty patch of sky simultaneously. Each telescope has its own unique design, its own mirrors and detectors with different strengths and potential systematic errors. By comparing their independent measurements of the background's intensity in that patch, scientists can triangulate the truth. If all three agree, confidence in the calibration is high. If one disagrees, it flags a potential issue with that specific instrument's sensitivity or its model of galactic absorption. This process is constant and meticulous, a behind-the-scenes effort that makes all the spectacular discoveries possible. So the background is far more than a subject of study. It is an essential piece of laboratory infrastructure. Its presumed stability, even as we question its origins, is the foundation upon which our entire understanding of the high-energy universe is built. We are balancing on a whisper, using its faint, steady tone to tune our ears to hear everything else. But the universe's most brilliant X-ray engines are not always found in the expected places. Scattered throughout nearby galaxies, far from the central supermassive black hole, astronomers find strange, isolated beacons shining with impossible ferocity. These are the ultra-luminous X-ray sources, or ULXS. They defy simple classification. They are hundreds to thousands of times brighter than any typical stellar mass black hole binary in our own galaxy, yet they are not anchored in galactic centers, so they are not supermassive. They exist in a perplexing middle ground, shining with the power of millions of suns but located in the galactic suburbs, often near star-forming regions. How can something so bright not be a supermassive black hole? The leading suspect is a long-sought cosmic missing link, the intermediate mass black hole. These would be black holes with masses between 100 and 100,000 times that of our Sun, filling the vast gap between the stellar mass remnants and the galactic giants. An object in this range, accreting matter at a furious rate, could theoretically produce the staggering luminosity we observe, but the physics of such feeding is extreme. It pushes against a fundamental limit called the Eddington limit, which is the maximum brightness an object of a given mass can achieve when radiation pressure from the infalling matter pushes back and prevents further accretion. To shine as brightly as they do, ULXS must be either violating this limit through some complex process like funneling material in a focused beam, or they must be more massive than they appear. Some may even be stellar mass black holes in a unique, super-efficient feeding mode, acting like cosmic gourmands consuming matter far faster than we thought possible. The mystery deepens when we consider their potential impact on the grand scale. Today, ULXS are rare oddities, but in the early universe, conditions were wildly different. Galaxies were smaller, gas was abundant, and massive star formation was rampant. This could have been the perfect nursery for a vast population of intermediate mass black holes, potentially creating an era where ULXS were commonplace. If that is true, then the combined X-ray light from all these brilliant, off-center monsters across cosmic time could have left a permanent signature woven into the cosmic X-ray background. Their light, stretched by the expansion of the universe, would now contribute to that faint, unresolved haze we still cannot fully account for. They represent a hidden chapter of black hole growth, a phase where monsters grew in the chaotic outskirts of infant galaxies before migrating inward to become the supermassive giants we know today. Finding their faint, collective echo in the background would be like discovering the fossilized footprints of a lost species of cosmic titan. The violent birth of stars is itself a source of cosmic X-rays. To find every contributor to the universal whisper, we must look beyond the obvious monsters to the stellar nurseries themselves. In galaxies undergoing furious bursts of star formation, the environment is not serene. It is a chaotic, energetic cauldron. Massive stars live fast and die young, exploding as supernova within only a few million years. Before their demise, these same stars blast out powerful stellar winds, streams of charged particles that rush outward at tremendous speeds. Both of these processes, the cataclysmic explosions and the relentless winds, inject colossal amounts of energy into the surrounding gas. This interstellar gas is heated to millions of degrees, creating vast bubbles and cavities of hot, diffuse plasma that permeate the galaxy's disk. And at those temperatures, this plasma glows in X-rays. This entire cycle is known as stellar feedback, a self-regulating process where the energy from stars heats and stirs the galactic gas, which in turn can either trigger new star formation or shut it down entirely. It is the galaxy's own internal weather system, driven by stellar violence. So, what is the X-ray signature of a single, vigorously star-forming galaxy? It is not a collection of brilliant points, but a more diffuse, extended glow emanating from its spiral arms and star-forming regions. This is the combined light from thousands of supernova remnants and the accumulated hot gas from countless stellar winds. Individually, such a galaxy is far less luminous in X-rays than an active galactic nucleus with a feeding black hole. But here is the crucial point: in the early universe, such galaxies were everywhere. During the epoch of cosmic noon, the universe was not just a time of quasar feasting, it was also a period of peak star formation. Galaxies were smaller, gas-rich, and churning out new stars at a rate far exceeding anything we see in the modern cosmos. If every one of those galaxies was filled with this hot, diffuse X-ray emitting plasma, their collective output across billions of years could be substantial. Quantifying this contribution is a complex task of cosmic accounting. Astronomers must estimate the typical X-ray luminosity of a star-forming galaxy, a number that is closely tied to its rate of forming new stars. They then must determine how many such galaxies existed at each chapter of cosmic history, especially at higher redshifts, meaning further back in time. The calculations suggest this stellar feedback component is indeed a measurable piece of the cosmic X-ray background puzzle. It likely contributes a few percent to the total intensity, a small but non-negligible fraction. Its importance, however, may be greater in shaping the specific energy or color of the background's light. The hot gas from stellar feedback tends to emit at somewhat softer X-ray energies than the furious processes around black holes. This means its fingerprint is subtly different. When we look at the deepest, most distant reaches of the background, we are looking back to when the universe was actively building its first generations of stars. In that ancient light, the relative whisper from these stellar nurseries might have been louder, a greater part of the chorus before the black holes fully awakened. Disentangling that specific signal is like trying to isolate the sound of rain from the roar of a river. It requires exquisitely sensitive telescopes and sophisticated models to separate the diffuse glow of hot galactic gas from the point-like glare of black holes and the vast haze of the intergalactic web. Yet this effort is vital. It completes the picture of cosmic evolution, reminding us that the background is not just a record of destruction, but also of creation. The same violent processes that forge new stars and planets also heat the galaxy, and that heat leaves a permanent, faint mark on the sky, a testament to the turbulent life cycle of matter itself. One spectral line has ignited a debate that cuts to the heart of modern cosmology. At a specific energy of 3.5 kilo-electron volts, a faint, persistent spike appears in the X-ray spectra of galaxy clusters and even in the all-sky background. This is the 3.5 kilo-electron volt line anomaly, and for a time, it was the most promising candidate for a direct dark matter signal ever seen. The reasoning was electrifying. If dark matter consists of sterile neutrinos, as some theories predict, then these particles could occasionally decay. A single sterile neutrino would vanish, transforming into an ordinary neutrino and an X-ray photon. The energy of that photon is determined by the mass of the sterile neutrino particle itself. A particle with a mass of around 7 kilo-electron volts, which splits its energy between the two decay products, would produce a photon at exactly 3.5 kilo-electron volts. This is a clean, testable prediction. The discovery of such a line uniformly across the cosmos would not just reveal the nature of dark matter, it would unveil a fundamental particle beyond the standard model. The initial observations seemed to support this breathtaking idea. Multiple independent teams analyzing data from different telescopes like XMM Newton and Chandra reported seeing this exact line in the stacked X-ray light from massive galaxy clusters like Perseus and Coma. Crucially, the line did not appear to come from the bright central galaxies where normal astrophysical processes are rampant, but from the diffused dark matter halos surrounding them. It was as if the invisible skeleton of the cosmos was faintly glowing at one precise color. The excitement, however, was met with immediate and intense skepticism. The signal was excruciatingly faint, sitting right at the limit of what our instruments could detect. The central challenge became one of contamination. Could this line be produced by something mundane, something made of ordinary atoms? The prime astrophysical suspect was potassium. Highly ionized potassium atoms, stripped of many of their electrons in the scorching plasma of cluster gas, can emit a complex series of lines. One of those lines sits very close to 3.5 kilo-electron volts. Distinguishing between a potential dark matter decay line and a potassium emission line is a monumental task requiring exquisitely precise measurements of the X-ray spectrum. It is like trying to tell if a distant bell is ringing a pure A note or a slightly sharp G sharp while standing in a roaring concert hall. Subsequent observations deepened the mystery rather than solving it. Some telescopes saw the line in certain clusters but not in others. Analyses of the Milky Way's own diffuse X-ray glow sometimes showed a hint of the line and sometimes showed nothing at all. The debate grew fierce, with papers published arguing passionately for both the dark matter interpretation and the potassium explanation. The issue highlights a fundamental tension in frontier science. When you are probing the very edge of detectability, systematic errors, the subtle, hidden biases in instrument calibration and data analysis can create signals that look real but are not. The 3.5 kilo-electron volt line could be the siren song of a new physics, or it could be the collective sigh of imperfect instruments and unmodeled atomic physics. As of now, the consensus has shifted. Most astronomers believe the weight of evidence points toward an astrophysical origin, likely from those complex potassium transitions. Yet the line has never been fully and definitively explained away. It remains an anomaly, a ghost in the data. Its legacy is profound. It forced the development of more rigorous methods for hunting such subtle signals, and it demonstrated exactly how we might one day find dark matter's fingerprint within the cosmic X-ray background. The hunt has not ended, it has simply become more sophisticated. We now know what to look for and how perilously difficult it is to see. The next anomaly, perhaps hiding at a different energy, may be the real one, waiting for a telescope with just a little more sensitivity to lift it from the universal whisper into the realm of undeniable discovery. Our ability to hear that faint cosmic whisper is about to take a quantum leap. The next generation of X-ray observatories, now on the drawing boards and launch pads, are not mere upgrades. They are revolutionary instruments designed to listen to the universe with ears we have never possessed before. Missions like Athena, Lynx, and XRISM represent a fundamental shift in our observational power, promising to transform the cosmic X-ray background from a uniform hum into a crystal-clear conversation. Their combined capabilities will be staggering. Imagine moving from a grainy, black and white photograph of a distant crowd to a high-definition video where you can see every individual face, their expressions, and even the colors of their clothes. That is the scale of the leap we are anticipating. The European Space Agency's Athena, the Athena X-ray Observatory, will feature a mirror with an unprecedented collecting area, meaning it can gather X-ray photons with phenomenal efficiency. It will also carry a revolutionary microcalorimeter spectrometer that can measure the energy or color of each incoming X-ray photon with exquisite precision. This is like giving a musician perfect pitch for the very first time, allowing them to distinguish notes in the cosmic symphony that were previously just noise. NASA Lynx concept takes a different, complementary approach. It is designed for extreme angular resolution, the sharpness of its vision. Lynx aims to see the X-ray sky with a clarity matching the Hubble Space Telescope's iconic views in visible light. It will peer so deeply and so sharply that it could resolve virtually every single point source contributing to the background, down to the faintest, most distant black holes in the universe. Meanwhile, the recently launched XRISM, a joint mission by JAXA and NASA, is already demonstrating the power of high-resolution spectroscopy, providing a taste of the detailed chemical and physical diagnostics that will become routine. Together, these observatories will launch a new era of discovery. They are poised to solve some of the most stubborn mysteries we have discussed. First and foremost, they will likely finish the job Chandra started, fully resolving the cosmic X-ray background into its constituent points of light. Lynx, with its eagle-eyed vision, is expected to pinpoint the vast population of heavily obscured active galactic nuclei and the earliest, most distant black holes, finally accounting for that lingering unresolved fraction. This will tell us definitively if the background is truly just the sum of countless point sources, or if a truly diffuse component remains. Second, and perhaps even more thrilling, is the hunt for the missing matter. Athena's superb spectral resolution is tailor-made to detect the warm-hot intergalactic medium. It will scan the seemingly empty spaces between galaxies, searching for the specific, faint X-ray absorption lines that will be imprinted on the light of distant quasars by the warm gas filaments of the cosmic web. Finding this signature would be the long-awaited solution to the missing baryon problem, a monumental achievement that would literally map the hidden skeleton of the universe. These telescopes will also dissect the puzzling emission lines and the high-energy tail of the background with forensic detail, potentially identifying new atomic transitions or finally ruling out or confirming exotic origins like sterile neutrino decay. They will watch the flicker of blazars and the flare of tidal disruption events with a clarity that reveals new physics. The future they promise is one of transformation, where the cosmic X-ray background ceases to be a monolithic mystery and becomes instead a finely detailed tool, a universal ledger we can finally read line by line. The whisper is about to become a shout, and within it we will hear the answers we have sought for decades. Before those brilliant quasars of cosmic noon, there was a deeper, more formative darkness. The universe's first billion years are often called the cosmic dark ages, an epoch after the primordial glow faded and before the first stars ignited. But that term is misleading because something was already stirring in the shadows. The seeds of the first supermassive black holes were taking root, and their birth cries, though faint, may have left a permanent scar on the light we see today. These are the elusive population, three black holes theorists propose, formed from the collapse of the universe's very first, unimaginably massive stars. Unlike stars today, these primordial giants would have been pure hydrogen and helium, free of heavier elements, allowing them to grow to hundreds of solar masses before collapsing directly into black holes. They would have been small by today's standards, but they were the pioneers. They began to merge to accrete gas in the dense, early galaxies, and over time, they grew into the monsters that would power the quasars we see a billion years later. Their activity, however faint and sporadic, would have generated X-rays, and because they existed at such tremendous distances, at such high redshift, their light has been stretched, diluted, and stretched again by the expanding universe. The individual X-ray photons from any single one of these first black holes would be incredibly feeble by the time they reach us. But if there were enough of them spread across the entire early cosmos, their combined output could contribute a unique, ancient layer to the cosmic X-ray background. This is not the light of mature quasars, but the faint collective spark of ignition. Detecting this specific signal is perhaps the ultimate challenge in X-ray astronomy. It is like trying to hear the first tentative notes of a symphony that began over 13 billion years ago, notes that have been drowned out by the roaring crescendo that followed. Our current telescopes, as powerful as they are, likely blend this primordial whisper into the unresolved haze we still cannot fully account for. It is buried in the deepest, most uniform part of the background. But the significance of finding it goes far beyond simply completing our census of X-ray sources. It ties directly into one of the great transformations in cosmic history, the epoch of reionization. After the Dark Ages, the universe was filled with a thick fog of neutral hydrogen gas. For light to travel freely, that fog needed to be burned away. The hydrogen atoms split back into protons and electrons. This process is called reionization. For decades, astronomers assumed the first stars provided the necessary ultraviolet radiation to do this job, but there is a problem. The harsh ultraviolet light from massive stars does not travel far. It is easily absorbed by the dense gas in their own stellar nurseries. Could the first black holes have played the decisive role? X-rays are the perfect tool for cosmic archaeology here. Unlike ultraviolet light, X-rays are penetrating. They can escape the dusty, gas-rich environments of early galaxies and travel vast distances through the intergalactic medium. When an X-ray photon encounters a neutral hydrogen atom in the vast cosmic web, it does not simply ionize it, it kicks out an electron, and that high-energy electron can then go on to ionize many more atoms along its path. A single X-ray photon could therefore clear a much larger bubble in the neutral fog than a single ultraviolet photon could. If the first black holes were numerous and active enough, their collective X-ray output could have been the primary catalyst for reionization, slowly and steadily cooking the universe clear over hundreds of millions of years. This idea reframes our entire narrative of cosmic dawn. It suggests the universe was not illuminated first by starlight, but by the ghostly, penetrating glow of its first hidden monsters. Their faint X-rays would have prepared the stage, creating ionized channels through which the later light of stars and brilliant quasars could finally shine. So the hunt for their signature in the cosmic X-ray background is a hunt for the architects of the transparent cosmos we inhabit today. The next generation of telescopes, with their phenomenal sensitivity to the very softest X-rays stretched from those early epochs, will scan the deepest parts of the background for this specific ancient fingerprint. Finding it would not just solve a mystery about the background's composition, it would rewrite the first chapter of our cosmic story, revealing that the violence of black holes was not a later development, but a fundamental force in shaping the light-filled universe from its very beginnings. That faint X-ray hum does not exist in isolation. It is part of a grand, multi-wavelength symphony of the cosmos, and the true power of its signal is unlocked only when we listen to it in concert with the others. This is the technique of cross-correlation, a statistical detective method that compares the faint patterns in the X-ray background map with maps of the sky made at completely different wavelengths. It is like taking two seemingly random sheets of static from different radio stations and discovering that when you overlay them, a hidden picture emerges. By doing this, astronomers can trace the origins of the X-ray whisper back to specific types of galaxies and environments, finally disentangling the overlapping voices in the cosmic chorus. The process begins with maps. We have a map of the subtle fluctuations in the cosmic X-ray background, those tiny anisotropies that trace the hot, energetic universe. Then we have other maps, deep infrared surveys like those from the Spitzer Space Telescope or the James Webb Space Telescope, see the warm dust and the faint glow of ancient stars. Optical surveys like the Sloan Digital Sky Survey map the visible starlight from billions of galaxies. And then there are maps of an entirely different kind, those of dark matter itself, created through the technique of gravitational lensing. When a massive object like a galaxy cluster lies between us and a more distant galaxy, its gravity bends and distorts the background galaxy's light, acting like a cosmic magnifying glass. By measuring these subtle distortions across the sky, astronomers can create a map of where mass is concentrated, revealing the invisible scaffolding of dark matter that underpins all structure. The cross-correlation magic happens when scientists take the X-ray map and mathematically compare it to, say, the infrared map. They ask a simple but profound question: do the spots where the X-ray background is slightly brighter also correspond to spots where there are more infrared galaxies? If the answer is yes and the correlation is strong, it tells us that the sources contributing to that part of the X-ray background are physically associated with the types of galaxies that glow brightly in the infrared. What does that mean in practice? A strong correlation with infrared bright galaxies points directly to heavily obscured active galactic nuclei. Remember, those are the black holes shrouded in thick dust. The dust absorbs the black hole's high-energy X-rays and re-emits them as lower-energy infrared light. So if the X-ray fluctuations match up with the infrared map, it is powerful evidence that a significant portion of the unresolved X-ray background is coming from these hidden, dust-enshrouded monsters. Similarly, a cross-correlation with optical maps of typical star-forming galaxies helps quantify the contribution from normal stellar processes, like the hot gas from supernova and stellar winds within those galaxies. Perhaps the most elegant correlation is with the dark matter maps from gravitational lensing. Dark matter dictates where ordinary matter gathers. The gravitational potential wells of dark matter halos pull in gas, which then forms stars and feeds black holes. Therefore, the places where dark matter is most concentrated should also be the places where X-ray sources, whether they are active galactic nuclei or hot cluster gas, are most abundant. By cross-correlating the X-ray background with these mass maps, scientists can test this fundamental prediction of our cosmological models. Does the X-ray light truly trace the underlying mass distribution of the universe? The answer appears to be a resounding yes. The fluctuations in the X-ray background align beautifully with the dark matter web, confirming that the violent, high-energy processes we detect are not random. They are a direct consequence of gravity sculpting the cosmos, with X-rays shining brightest where matter is most densely packed. This technique goes beyond simple identification. It allows for a kind of cosmic accounting. By measuring the strength of the correlation with each type of map, astronomers can assign percentages. They can say, for instance, that roughly this much of the unresolved background correlates with infrared galaxies, meaning it likely comes from obscured black holes. That much correlates with lensing mass, meaning it traces the hot gas in dark matter halos. And this remaining fraction does not correlate strongly with anything we have mapped yet, pointing to a truly diffuse component, perhaps the long-sought warm-hot intergalactic medium. It is a statistical way to separate the blended voices, to hear the individual instruments within the orchestra. Without ever resolving a single faint source, cross-correlation tells us who lives in the neighborhoods responsible for the glow. It confirms that the universe's X-ray whisper is the sound of structure itself, a direct echo of gravity's work, heard most clearly when we listen to the cosmos with all our senses at once. The ultimate test of our understanding is not a single observation, but a grand simulation of cosmic history. To explain the precise intensity and spectrum of the cosmic X-ray background, scientists must do more than just catalog sources. They must build a universe from scratch inside a supercomputer. These are the synthesis models, vast digital engines that attempt to replay 13.8 billion years of cosmic evolution, governed by the laws of physics as we know them. The goal is deceptively simple: to produce a simulated sky that matches the X-ray whisper we actually observe. The process begins with the smooth, hot conditions of the early universe, just after the cosmic microwave background was released. Into this digital primordial soup, the models seed tiny fluctuations in density, the seeds of all future structure dictated by dark matter. Gravity then takes over, causing these seeds to grow. Dark matter halos form, and within them, gas condenses, cools, and forms the first stars and galaxies. The models must then incorporate recipes for every process we have discussed: the birth and merger of supermassive black holes, their feeding frenzies as active galactic nuclei, the obscuration by dust, the heating of gas in galaxy clusters, the feedback from supernova and stellar winds, and the expansion of the universe itself. It is a staggeringly complex ballet of physics, chemistry, and chance, all computed over billions of virtual years. The final output is a prediction, a detailed map of what the X-ray sky should look like today, in terms of both its total glow and the specific points of light within it. This is where theory meets observation in a direct, unforgiving confrontation. For decades, there was a glaring mismatch. Early synthesis models consistently predicted a cosmic X-ray background that was far too bright. The simulated universe was, in essence, too violent. It produced too many active black holes shining too brightly, especially in the distant past. This was a profound clue, telling us that our recipes for black hole growth and feeding were wrong. Something was suppressing the activity of these monsters, or perhaps limiting their fuel supply. The solution came from incorporating a crucial piece of physics: feedback. The models began to include the tremendous energy output from the black holes themselves. As a supermassive black hole feeds and becomes a brilliant quasar, its radiation and powerful jets blast outward, heating and dispersing the very gas reservoir that feeds it. This self-regulating process, like a furnace that automatically shuts off when it gets too hot, prevents the black hole from eating everything at once. It forces the black hole to grow in fits and starts, with long periods of dormancy between brief, brilliant feasts. When this feedback was added to the simulations, the predicted X-ray background dimmed dramatically, coming into much closer agreement with the real, observed whisper. It was a triumph of computational astrophysics, showing that black holes are not passive consumers but active architects of their own environments. Yet disagreements remain, and these gaps are the signposts to our ignorance. One persistent issue lies with the very first black holes. Synthesis models struggle to explain how supermassive black holes grew so incredibly massive so quickly in the early universe. Our standard recipes for gas accretion and mergers often cannot grow a billion solar mass monster in less than a billion years. This suggests we are missing a key ingredient in those primordial epochs, perhaps a population of massive seed black holes from the direct collapse of giant gas clouds, or a more efficient mode of feeding we have not yet accounted for. Another gap appears in the details of the obscured population. While models now include dusty shrouds predicting the exact number of heavily obscured active galactic nuclei, and their distribution across cosmic time is difficult. The real universe seems to have a specific mix of hidden versus visible monsters that our simulations do not yet perfectly reproduce. This tells us our understanding of the gas and dust in galactic centers is still incomplete. Furthermore, the models have trouble fully accounting for the high energy tail of the background and the exact shape of its spectrum. This could point to an undercounting of certain types of sources, like the ultra-luminous X-ray sources or the particle acceleration in cosmic shockwaves, or it could hint at something more exotic lingering in the data. Each discrepancy is not a failure but a guide. When the synthetic sky does not match the real one, it forces scientists to question their assumptions. Is the recipe for star formation wrong? Are we misunderstanding how gas flows into galactic centers? Could there be a contribution from decaying dark matter that we have not included? The synthesis model becomes a laboratory for testing wild ideas, a sandbox for the cosmos. By tweaking the virtual physics and comparing the new output to the actual cosmic X-ray background, researchers can rule out some possibilities and strengthen others. This iterative process, this constant conversation between digital universes and real telescopes, is how we slowly, painstakingly write the true story of our own. The faint X-ray hum is the final exam, and our synthesis models are our best attempt at showing our work. But a final, foundational mystery questions the very nature of that whisper itself. We have built our entire understanding of the cosmos on a bedrock principle, the cosmological principle. This states that on the largest scales, the universe is homogeneous and isotropic. Homogeneous means matter is evenly distributed, like the consistent texture of a well-mixed cake. Isotropic means it looks the same in every direction. This principle allows us to believe that our local view of the cosmos is not special or unique, that the laws of physics are universal. The cosmic X-ray background has long been considered the ultimate proof of isotropy, a perfectly uniform glow from all directions. But is it truly the same everywhere we look? The startling answer is maybe not. And if it isn't, it forces us to reconsider one of cosmology's most sacred assumptions. The hunt for deviations, called large-scale anisotropies, is a search for cracks in the foundation of our cosmic worldview. One expected deviation comes from our own motion. Our solar system, our galaxy, all are moving at a brisk pace through the cosmos. This motion, like running through a gentle rain, should create a subtle dipole pattern in the background. Imagine standing still in a snowfall. The flakes fall evenly all around you. Now start walking briskly forward. More flakes will hit your face than your back. The snowfall appears anisotropic from your moving perspective. Similarly, as we move through the sea of X-ray photons that make up the background, we should see a slight enhancement in brightness in the direction we're heading, and a slight dimming in the direction we're leaving behind. This kinematic dipole is predicted and has been measured with stunning precision in the cosmic microwave background. Finding a matching dipole in the X-ray background would be a powerful consistency check, confirming our motion through this later epoch of cosmic light. But the results are puzzling. Some studies suggest the X-ray dipole is there, but its amplitude and direction do not perfectly align with expectations from our measured motion. This discrepancy is a small but persistent thorn. Could it be a sign that the X-ray sources themselves are not evenly distributed in the universe? That would be a far more profound discovery. It would mean that on the very largest scales, the universe has a preferred direction, a lopsidedness in the distribution of violent events and hot gas. Perhaps one hemisphere of the cosmos simply has more supermassive black holes or more massive galaxy clusters than the other. Such a finding would directly challenge the isotropy part of the cosmological principle. It would suggest that our cosmic neighborhood is in fact special, located in a region of higher or lower X-ray activity than the universal average. Other searchers have looked beyond a simple dipole for even more complex patterns, vast swaths of sky that are inexplicably brighter or fainter. These could be echoes of ancient, unimaginably large structures, like superclusters of galaxy clusters on scales so vast they defy our models of how quickly structure could form after the Big Bang. The technical challenge here is immense, as distinguishing a genuine cosmological anisotropy from the foreground fog of our own galaxy's emission is a Herculean task. Every claimed detection is met with rigorous scrutiny as the implications are so revolutionary. So far, the evidence is tantalizing but not conclusive. The background appears remarkably isotropic but with intriguing whispers of something more. This final mystery brings us full circle, back to the fundamental question of our place in the cosmos. Is the universe a truly even and balanced tapestry, or does the faint X-ray glow reveal a hidden grain, a direction to the void? The answer lies in the most subtle variations of a whisper we are only just learning to hear, a whisper that may tell us whether we live in a cosmos of perfect symmetry or one of grand, lopsided design. This faint universal whisper is not a single riddle, but a tapestry of 25 interconnected mysteries. From its accidental discovery to the unresolved glow, from the hidden monsters and missing matter to the spectral lines with no name, each puzzle interlocks with the next. The cosmic X-ray background is far more than astronomical noise. It is the universe's own archival record, a permanent testament written in the language of high-energy violence. It chronicles the rise of the first black holes, the collisions of galaxy clusters, the searing heat of the cosmic web, and the possible decay of dark matter itself. Every photon in that haze carries a story from a different chapter of cosmic history, a story of gravity's relentless work and matter's most extreme transformations. This journey through its secrets reveals that our quiet, star-filled night sky is an illusion. Beneath the visible calm rages a hidden universe of perpetual fury, and its afterglow surrounds us all. The future of X-ray astronomy promises to turn this whisper into a clear voice. With observatories like Athena and Lynx on the horizon, we stand at the threshold of a new era. We will map the warm, hot intergalactic medium, resolve the final unseen sources, and perhaps even capture the definitive fingerprint of a new particle. The archive is about to be opened fully, and its contents will redefine our place in the cosmos once more. Your curiosity is the engine of this exploration. Which of these 25 mysteries captures your imagination the most? Is it the ghostly 3.5 kilo electron-volt line, the hidden population of obscured black holes, or the profound idea that black holes lit up the cosmic dawn? Share your thoughts below, and if you hunger for more journeys into the unseen, subscribe to continue unraveling the universe's greatest secrets with us. The cosmos is speaking. We are only just learning how to listen.